In this problem, the matrix A is diagonal. Every entry off the main diagonal from the upper left to the lower right is a 0. The numbers on the main diagonal from upper left to lower right are non-zero. They don't have to be non-zero. They could be 0, but in this case, they're non-zero. Here's the differential equation we're trying to think about, drawing the phase plane for, identifying straight line solutions for, and also identifying eigenvalues and eigenvectors for. Figuring out the solution is supposed to be the easiest part because it's completely decoupled. That's what happens with diagonal matrices. That's why they're nice. dx dt is ultimately just 2x. So the general solution for x is c times e to the 2t. And dy dt is ultimately y over 2, 1/2 y. So its general solution is ultimately c times e to the t over 2. With these initial conditions, x naught and y naught, those are going to be the c's. So your solution, which you could write with the book's notation, y of t like this, or you could use my capital Phi notation if you wanted to, is x naught e to the 2t for the first component and y naught e to the t over 2, or if you prefer, e to the 0.5 times t for the second component. Okay, so there's your, if you think of x naught and y naught as fixed, this is a unique solution of this initial value problem. Draw the phase plane is the next thing. And try to identify straight line solutions, solution curves that are straight. And you can think about null lines here, but it's a little funny, little unusual, because the x null line happens to be the y-axis, which it can't really, solutions can't really cross the y-axis with vertical tangents. They have to effectively stay on the y-axis with vertical tangents. The y-axis is going to be a straight line solution. The x null line is where the right-hand side of the dx dt equation is 0, which is where x is 0, which is the y-axis. All along the y-axis, dx dt is 0. So if your initial condition is on the y-axis, it's got to stay on the y-axis for all time. If x naught is 0, then the first component is always 0. And the second component is y naught e to the 2 t over 2, which is exponential growth away from 0. So in the y direction, the equilibrium point, which will be at the origin, will be a source in that direction. The y null line is the x-axis in this example. This kind of thing happens with diagonal matrices. Y over 2 is 0, which is equivalent to y equals 0, which is the x-axis. Here's x, here's y. And if you start on the x-axis, that means y naught is 0. The second component is always 0. And the solution, the first component, is still exponential growth. It's also a source in the x direction. So overall, it's a source in 2 dimensions. Solution curves have to move away from it. Now, these are evidently straight line solutions because if you start on one of these axes, you're going to stay on one of these axes. Are there any other straight line solutions? It turns out no. If you try to draw more of the phase plane by hand, it is a bit tricky. You can try to draw some vectors in the vector field. For example, if you want to draw the vector in the vector field at the point 1, 1, what would you get when you plug in x equals 1 and y equals 1 there? You'd get the vector 2, 1/2, which would be more pointing to the right than it would be pointing upward. And it gets more extreme as x gets bigger, but y stays constant. For example, if x is 2 and y is 1, then this becomes 4, 1. It gets even more almost horizontal. That I didn't make much of a distinction between those. As x gets close to 0, then the x component gets close to 0, and the vectors get a bit more vertical looking. You could continue drawing more vectors in the vector field. If you drew enough of them to get a feel for what the phase portrait looks like, or if you use stream plot in Mathematica, you're going to get solution curves looking like this. So if you were able to do that without technology, I salute you. That's pretty good. On the other side, they end up looking like this. Another reason why this should make some intuitive sense is because as t goes to infinity, the first component, e to the 2t, is going to grow a lot faster than the second component, e to the t over 2, because the coefficient of t is bigger. So the solutions ultimately, as t gets larger and larger, have to grow to infinity faster in the x direction than they do in the y direction. They still go to infinity in the y direction, but just not as fast as in the x direction. So this ends up being what the solution, the phase portrait looks like. And yeah, the straight line solutions are along the axes. How is this related to eigenvalues and eigenvectors? The definition of an eigenvalue is a number lambda. This is just the traditional letter used for eigenvalues. Lambda is an eigenvalue of the matrix A. This is a definition. If there exists or there is a non-zero vector V called an eigenvector, so I'm kind of defining the eigenvectors here as well, of a, for the eigenvalue lambda. That's a parenthetical remark that is essentially defining eigenvector. Not quite. If A times V equals lambda times V. It's very important that you don't misunderstand what this equation is saying. Or another way to say it is to fully understand what it's saying. Both sides of this equation are ultimately vectors. Here I've got a matrix A times the vector V. That's a vector. Here I've got a scalar, a number, lambda times the vector V. That's a vector. Yes, this is a matrix. Yes, this is a vector. Yes, lambda is a scalar. And once again, V is a vector. But whether you do A times V or lambda times V, the end result is a vector. Don't think you can take this equation and cancel the V's to say A equals lambda. Not allowed. A is a matrix, lambda is a number. But if this is true for some non-zero vector and some number lambda, that should seem kind of special. That should seem unusual. And it is unusual. How is it related to the differential equation and the phase plane? The eigenvectors correspond to straight line solutions. Why? Intuitively, because when you think about the differential equation written in vector form, dy dt equals a times y. The right-hand side does define a vector field. I could call it f of y. Vector f of vector y. It is a linear vector field, but it is a vector field. And when you say V is an eigenvector for the eigenvalue lambda, you're effectively saying that if I plug V into this equation in place of y, I get a scalar multiple of itself. The output is a scalar multiple of the input. Now, we typically think of inputs of vector fields as points and the outputs as arrows. But we could think of the inputs as being arrows based at the origin. If I plug in a vector based at the origin parallel to the x-axis, like this vector that I'm drawing without actually drawing it, what vector do I get out? I get another vector out parallel to the x-axis. It's a scalar multiple of itself. the output of the vector field is a scalar multiple of the input, some stretch. Or maybe if the lambda is negative, it also includes a reflection of itself. It's parallel to itself. That's what it's the same. A, V, and lambda V are equal, and therefore they're also parallel to, and they're also parallel to V itself, because it's a scalar times V. And that's what happens with straight line solutions. The vectors in the vector field are parallel to, in this case, the axes. They're along the straight line solutions. That's why it's important. So what are the eigenvalues and eigenvectors in this case? Well, the eigenvalues turn out to be the numbers that are the coefficients of t, the 2 and the 1/2. And the eigenvectors are, well, any non-zero vector parallel to the x-axis for the eigenvalue 2 and parallel to the y-axis for the eigenvalue 1/2. Any such non-zero vector is an eigenvector. So the e-values here for this example are 2 and 1/2, and the corresponding e-vectors for 2, it's any vector, non-zero vector parallel to the x-axis, like 1, 0. And for 1/2, it's any non-zero vector parallel to the y-axis, like 0, 1. Oh, those form a basis for the plane basis. In fact, the standard basis, I hat and j hat. Well, that's because the matrix A is diagonal. That's why it turned out so simple. If the matrix A is not diagonal, then it's not so simple. Very important, you realize this eigenvector corresponds with that eigenvalue, and this eigenvector corresponds with this eigenvalue. This eigenvector is not an eigenvector for that eigenvalue. This eigenvector is not an eigenvector for that eigenvalue. They got to get paired together. What the textbook emphasizes is that you can write the general solution of the differential equation this way. Y of t, say, equals an arbitrary constant that the textbook typically calls K1 instead of C1. K1 e to the 2t times the eigenvector corresponding to the eigenvalue 2, plus another arbitrary constant, K2 e to the t over 2 times the eigenvector corresponding to the eigenvalue 1/2. That's the book's way of writing the general solution. K1 and K2 are arbitrary here. If I've got an initial condition, even a generic initial condition, x naught, y naught, I'd have to solve for K1 and K2. In this case, it's fairly simple. The vector whose components are little x naught, y naught, which is the vector capital Y naught, is y of 0. E to the 0 is 1. That's a 1. This is a 1. My system of equations to solve for K1 and K2 is very simple. K1 equals x naught, K2 equals y naught. We already knew the answer. In general, if your eigenvectors are not I hat and j hat, if they're not the standard basis, then solving for K1 and K2 is more complicated. You got to solve a system of linear equations with row reduction. With diagonal matrices, things are simpler. This is related to the matrix exponential. This does turn out to equal e to the TA times the vector y naught, because e to the TA ends up being a diagonal matrix itself. E to the 2t, 0, 0, e to the t over 2. I'm not going to explain why at the moment, but that's what it does end up being. It is related to the matrix exponential and the beautiful generalization. And you can relate this to flows, but I'm not doing that today. You can relate this stuff to more abstract vector spaces as well. Yes, these eigenvectors form a basis for the plane R2. These two functions of t form a basis for the solution space of the differential equation. Notice any solution is a linear combination of them. They span. And they are linearly independent as functions of t. They're not ordinary functions, right? Because they're vector functions. They're parametric curves. But you can think about vector functions as being functions too, and elements of function spaces that are vector spaces. Let's go look at the corresponding difference equation as well. As far as solving it, you solve differential equations by integration. You solve difference equations by iteration. But it is still completely decoupled. So you can think about each of these by themselves and then just put the answer together in a vector. We've done this before. Xn is 2xn minus 1, but xn minus 1 is 2xn minus 2. So this is 2 squared times xn minus 2. But xn minus 2 is 2 times xn minus 3. So this is 2 cubed times xn minus 3. Assuming this pattern holds, we relate this to x naught, we're going to get the power of 2 matching what I'd have to subtract from n to get 0, and that would be an n, 2 to the n. And a yn is going to be something similar, except instead of a 2, it's a 1/2. Write it that way. You could also, since 1 to any power is 1, you could also write it this way. Put those together in a vector, and you've got your solution of the initial value problem. Write it as a vector xn, whose components are scalar xn and scalar yn. 2 to the n times x naught. I'll write it as 1/2 to the n. 1/2 to the n times y naught. This can be thought of as a matrix times a vector as well. The matrix whose entries are 2 to the n, 0, 0, and 1/2 to the n times the initial condition vector x naught, y naught. That's not the matrix exponential. No e's. But it is a to the nth power. It's a power of the matrix A. I didn't expect you to do that, but that's true. It's easy to figure out when A is diagonal. You just take, it's a new diagonal matrix whose entries on the main diagonal are the original entries of A to that same power. This doesn't happen so simple with non-diagonal matrices. That's why we have to do all the other stuff with the eigenvalues, eigenvectors, and coordinate changes, and change of coordinates matrices, which I'm not talking about today. But it's all related to dealing with non-diagonal matrices, effectively to relate them when you can to diagonal matrices. It's called diagonalization is the official name for it. Can we draw the phase plane? We've never really done this with difference equations before. Well, solutions, effectively, they are discrete points. N is a whole number here. First 0, then 1, then 2, then 3, etc. Do notice if y naught is 0, if we start on the x-axis, there say, if y naught is 0, then y stays 0, and we get 2 to the n x naught for the x component and 0 for the second. 2 to the n grows to infinity as n grows to infinity. The points got to move away from the origin, and they're all staying on the x-axis. The x-axis you could maybe call a straight line solution, even though the points themselves are discrete points. It's not a curve, it's a set of points. It's a sequence is the official name. If x naught were negative, you're still growing off to infinity. Should I draw arrows? Well, you could, but realize that it's not parametric curve, it's sequence, discrete points. But the arrows do remind you that they're going off to infinity. But something different happens along the y-axis than with the differential equation. If x naught is 0, then the x component is 0 always. But the y component even though 1/2 is positive, is decaying to 0, right? 1/2 to the n gets smaller and smaller. 1/2 squared is 1/4. 1/2 cubed is 1/8. This is going to 0. Points on the y-axis, they stay on the y-axis, it's a straight line solution, but they're heading towards 0. How'd that happen? Shouldn't it be just like the differential equation? No, it's not. It's not. It's similar in some ways, but it's not the exact same kind of thing. What's happening for initial conditions that are not on either axis? Say we started here at 1, 1, plug in x naught, y naught is 1. Well, the x coordinate goes to infinity and the y coordinate goes to 0. This is going to head off to the right forever and ever, but it's also going to go toward the x-axis. Should I connect the dots with a curve? Some people do. If you do, you got to keep in mind it's not really a solution curve. It's not a parametric curve, but it does help like draw an arrow. I'll do it very lightly. Maybe a different color. The purple dots are the true solutions points, the sequence, but drawing a curve connecting the dots helps you draw an arrow on top of it, indicating what direction the points are moving as n increases. But the red curve is not really a solution because that's a curve. Points over here go off this way, points down here go off this way, points over here go off this way. So it's like this is a source in the x direction, but a sink in the y direction. And the origin is an equilibrium point. If you start at the origin, you're going to stay at the origin. But it's an equilibrium point in the discrete sense, iterating the difference equation. So yes, the similarities, but differences. What are there? Are the eigenvalues and the eigenvectors the same? Yeah, actually, the eigenvalues and eigenvectors are the same. E values are still 2 and 1/2, and the E vectors, the corresponding E vectors, are 1, 0, and 0, 1. But the way they behave with regard to solutions is different. The 1/2 corresponds to exponential growth for the differential equation, but it corresponds to exponential decay with the difference equation. Weird, but true. You have to have well, I'll talk more about that later. What about the general solution? It's not in our textbook because the textbook focuses on differential equations. But I talk about this in the lectures. You could write the general solution for yn as k1 2 to the n times 1, 0 plus k2 1/2 to the n times 0, 1. Instead of doing e to the 2t and e to the 1/2 t, you do 2 to the n and 1/2 to the n. And once again, if you've got an initial condition, you can solve for k1 and k2 using the fact that any number to the 0 power is 1. Well, actually, that's not true for 0 to the 0 power, but ignore that. And this simplifies quite nicely to k1, k2, and therefore k1 and k2 are x naught and y naught, but we already knew that. Again, if your matrix is not diagonal, it gets more complicated. Solving for k1 and k2 involves a system of linear equations that you got to solve by row operations. So how do you find eigenvalues and eigenvectors in general? It's the last thing I'll say, then you can do some work. You got to solve that equation for A and for lambda and V effectively. It turns out that equation is equivalent to this equation, where I is the 2 by 2 identity matrix. You're looking for non-zero solutions for V, so you're looking for values of lambda that make this matrix here. non-invertible, you want the determinant of that matrix to be 0. You want the matrix to be singular, which means not invertible, special. And when it's not invertible, that's when it's going to have a non-trivial null space. So there will be non-trivial solutions for V of this homogeneous equation. Okay. Everything is starting to come together here in this week before the next exam.